yeah, these pictures are interesting pictures of detecting subatomic particles and their movement. So how the heck did they get these weird pictures? Well, there's two different types of chambers that they use to take pictures. Basically, you know, okay, so some of you suggested maybe it's a snail. All right, well, how would you tell if a snail was, you know, walking around? Do you remember when we did our slug slime thing? Well, you could see, you know, when the slugs escaped, and they had their trail of slime everywhere, right? Remember that?
I remember watching the videos and they glow and it sucks and you
Oh yeah, that too. Okay. but how did we see that? Okay, we tracked. We noticed their tracks, right? When you see, say you're trying to trap a bunny, you find its tracks in the snow and you place the trap around where it's you know, moving and stuff. Okay. Little bunny foo-foo walking through the forest. There. Okay. So so my pastor, he teaches kids, you know, the bunny foo-foo song, but you know, little bunny foo-foo walking through the forest, scooping up the field mice. Okay. So he taught them that, but he's like, I don't know, but taught them like a more realistic version, and halfway through the song they go snare, and it's like we cut the. Anyways, so now it's a joke in my head, but now I shared it. So okay, so how do physicists detect these radioactive decay when some of the particles and antiparticles are so small in size and mass? Because, you know, like a bunny, it's big, you can track it, but how do we track a positron or an electron? Well, what? I mean, pardon me? Okay. So physicists use tracks, just like in the examples we talked about, tracks left behind by subatomic particles to identify the type of particles and how particles interact with other particles. So here is a diagram of radioactive material. And look, there's some going straight across, there's some spiraling, there's some being shot off in different directions. This one seems to be going like we tracked it, it'd go in a whole circle, you know, but that's its shoot of its radius. Some are spiraling. So the way that they are behaving in that environment, and it's actually a magnetic field that's placed there, so yeah, you have the parallel plates and they're being shot through. So it's a normal kind of parallel plate observing a particle moving, but how do we actually see it? Because you can't see an electron. So what they use is something called a bubble and cloud chamber. So one, it detects like bubbles, and the other is detecting clouds. Okay, so they're kind of the opposite in each other. So the first one we'll do is a cloud chamber. Contains dust-free air supersaturated with vapor from a liquid such as water or ethanol. A charged particle speeding through the supersaturated air will ionize some molecules along its path, leaving behind a path of mini clouds. So think about it like, you know, watching a jet plane go across, you know, you see the puffs of air that it leaves behind. If you look at a jet plane, you can see the jet stream, right? You can see it leaving behind. So that's kind of the same thing, is it leaves behind these little puffs, okay? And so, because it's changed the air around it. So here, if we looked at it, what would happen is, so here would be like the radioactive source, and it's shot through, and in the cloud chamber is a magnetic field. So here it's showing that the magnetic field is coming out. The dot is out. So if it's coming out, so our thumb, it's going that way, right? That's the direction of the charged particle. It's coming out towards us. So if I'm using my left hand, the things that are being forced up would be negative, right? That's why it has, well, this would be like a beta negative, okay? And then the things, so if I had used my right hand, the things that are being forced down are positive. So that's why this one would be alpha. Now the one that's going straight across is gamma, because a gamma is just a photon, right? So it doesn't have a charge. So we don't really see its tracks necessarily, but we see it when it collides with an electron. So that's the cloud chamber. So next is a bubble chamber. Now it's really similar concept. It still uses the magnetic field thing, but instead of looking at clouds, you look at bubbles, okay? So bubble chambers reverse the process used in cloud chambers. Particle tracks are formed by a liquid turning into vapor instead of vapor turning into liquid. So bubble chambers contain liquefied gas on the verge of boiling. When charged particles zip through the liquid, the ionized molecules cause the liquid to boil, leaving a trail of tiny bubbles. Now, here's an important note that anything that's neutral, or is like, so any EMR or any neutral particles do not create tracks in a cloud or bubble chamber. They can still be shot in and interact or break down, but we can't see them coming in initially. So here is another kind of diagram, or another picture showing radioactive activity. And so you can see there's a lot of spiraling, lots of different things going on here, okay? But for them, so and this is an example of what a bubble chamber would look like. Now, you don't need to remember exactly how they all work perfectly. What we're mostly going to focus on is like when we look at the picture, and we know that it's under a magnetic field. Both are under a magnetic field. How can we determine the nature of the particles? So let's get into that then. So applying a magnetic field across the chamber causes charged particles to follow curved or spiral paths. The radius of the curvature can be used to determine the charge to mass ratio. Because if it's going in a circle based on the inducement of a magnetic field, we can say that Fm is equal to Fc. So if we expand that to say QV B perpendicular is equal to mv squared over r, I can simplify by crossing off two of the v's there. So then I have QB perpendicular is equal to mv over r. Now what I want to do is I'm going to set up kind of how mass is related to my r. So I'm just going to put the r, I'm going to multiply it, put it over here. So QB perpendicular times r is equal to m times v. Now, there's a lot going on here, but if we have our magnetic field stay the same, what's different about the particles coming in is their charges and their masses. So what we can see is if our mass of our object increases, our radius will increase. So they're proportional to one another. Now, we can also make observations about its speed or charge. But what is most significant, okay, really important, what is most significant about the nature of the particle and how it moves is mostly determined by its mass and charge, okay? So the mass, so if something is heavier, it will have a different type of radius. And so I'll go through this more. So the left-hand rule is used for negatively charged particles, and the right-hand rule for positively charged particles. It can be used to determine the nature of the charged particle. So So let's look at this diagram briefly now. So we know that like all of the incoming radiation is like from this side of the page. So our thumb is always going to go this way, and we're told that it's coming out of the page. So the circle means coming out, right? So let's use our right hand first. So if we it's coming in this way and it's coming out of the page. So anything that's being forced down is positive. So then I can say, okay, well this is definitely a positive object. I'm not going to claim if it's proton or positron right now. Here we're already told this is a gamma ray. It's undeflected, right? And then, okay, so let's try with these ones. So it's coming in, it's coming out of the page. There we go. It's being forced up, so these ones are negative. Okay, so what we can probably say, just looking at the differences in radiation from this one to this one, or not radiation, of radiuses, this radius is larger. Agree? Like if I made this a whole circle, this radius would be larger than these. Yeah? Okay. So that means since its radius is bigger, its mass is larger. So compared to, say, my options are like an electron, a positron, and a proton, the most massive of those three is a proton. So this is probably a proton. Because it could also be a positron, but a positron is only like the mass of an electron, right? So it's smaller. So this one could probably be, like, this might be an electron, and they might both be electrons. If one has more energy than the other, it can have a larger radius, like if its speed is more. But we won't deal as much with those ones, so let's just focus. Yep. With your hands. For this one, use your left hand, right? So if it's coming in, your fingers go toward you. Pardon me? This one? So this one only works if I use my left hand, because my thumb needs to be going to the right. Your fingers need to be coming toward you, and so my palm is going up. So since that works with only my left hand, then that must be a negative particle. Yeah. Okay, now another kind of, oopsies. An interesting one is if something is spiraling. So in some of our diagrams we saw that kind of spiral effect. Well, that's different than just a circle, right? If we have a complete circle, the circle doesn't get smaller, right? But a spiral, obviously it gets smaller and smaller. So what's happening to that particle if it's spiraling? Remember when we talked about the flaws of some of the atomic models? It's losing energy. Yeah, remember we said, like, if the electrons were circling around the nucleus in an orbit, they would be releasing EMR. And if that was the case, they would spiral in, right? So when we see something that's spiraling, a charged particle that spirals, it means that it's losing energy, okay? So the spiraling path indicates that the particle is losing kinetic energy. So it could be slowing down, or it is undergoing particle annihilation. So let's kind of go through what this would look like. So, and there's no calculations really involved in this this lesson. Yeah. So three types of subatomic particles that do not leave tracks in a bubble chamber. So we already talked about one, the gamma. So that's our gamma 0, 0, and our neutrons would be N1, 0, and our neutrinos. And my symbols for those are my V, 0, 0, and V, 0, 0. So both of them, notice the bottom number is 0, right? Because that bottom number, think about it almost like your charge. Okay? Okay, so now describe and explain the differences in the tracks made by the bubble chamber by the particles in each pair. So this is to kind of help you analyze how would the pattern look different. So say we compared a proton and an alpha particle. Well, say they would have the same direction, so same direction because both positive, but alpha would have a larger radius because more massive, meaning it has more mass. Because if you think about it, we have our alpha is 4 and 2, and our proton is 1, 1. Okay? So the alpha particle would have, say they're both going in this direction, it would have, say, a radius like that, but the proton could be like that. So it's just the curve would be smaller with the proton than with the alpha. So protons and electrons. So they would have opposite direction of movement because opposite charge, and a proton would have larger radius because it's more massive. So, because our proton mass, I should say m of p, so our proton mass is 1.67 times 10 to the negative 27, is that right? Yes. But our mass of our electron is 9.11 times 10 to the negative 31. So the proton, even though it's like really small amount, the proton is more massive. So say, yeah, I want to show you. Okay, then positron, oopsies. Okay, positron and proton. Same direction because charge, they're both positive, okay? But a positron, remember that's a beta particle, and a proton. So a proton, again, will have a larger radius because it's more massive. So most of your workbook is going to be like looking at a diagram and determining which path is which particle. So that's why I'm giving you kind of trying to give these examples. So positron and beta, and negative beta. So we have our positive and our negative. So these are both the same mass, so that will mean the same radius, but they're a different charge, so they'll be going in opposite directions.